Before a single piece of heavy machinery is deployed, we have to account for environments thousands of meters underground, vast spaces defined by extreme pressures, ancient rock layers, and trapped pockets of fluid. For decades, the core challenge of the energy industry has remained the same: navigating this world without a direct line of sight. Early geologists relied on surface-level topography and manual mapping to estimate what lay beneath. They used the visible curves of the landscape to project the likely path of buried structures. The only way to confirm those projections was by extracting physical rock cores. Each small, fragmented sample offered a tiny window into a massive, unseen formation. But as modern energy fields plunge deeper and become more structurally complex, the volume of geological data gathered during exploration has exceeded the capacity of traditional manual analysis. Relying on these fragmented physical records to make multi-million-dollar drilling decisions creates significant financial and operational risk, necessitating a move toward a unified digital environment that can reconcile every data point simultaneously. The first step in building this digital model is 3D seismic imaging, a technology used to map the underground without breaking the surface. The process begins with specialized vehicles that send concentrated, low-frequency vibrations deep into the Earth's crust. As these acoustic waves travel downward, they reflect off different rock strata. Those reflections travel back to the surface, captured by an array of sensors. The system translates the timing and intensity of those signals into a high-fidelity, three-dimensional geometric map of the underground formations. This provides the structural shape of the container, but it doesn't yet explain the nature of the fluids trapped within it. To understand the contents, OmniPetro merges the seismic map with historical well logs and data on rock porosity, the volume of empty space within the stone, and permeability, which is how easily fluid can move through those spaces. Here, digital geology applies physics to the structural map. At a microscopic level, we see the specific pore spaces where hydrocarbons reside. The system models the movement of oil, gas, and water through these tiny pathways, calculating how they interact under different conditions. By adding pressure and temperature variables to these fluids, the static map becomes a dynamic simulation of how the reservoir actually behaves. This integrated data framework allows engineers to observe the subsurface environment and its potential production characteristics long before a single drill bit touches the ground. To find the most efficient path into the simulated environment, OmniPetro utilizes AI reservoir prediction. The AI simulates thousands of future scenarios in seconds, testing how pressure levels and fluid volumes shift as the field is produced over several years. It tests hundreds of virtual drill paths against these scenarios, predicting flow rates and identifying potential hazards. Discarding paths that fail safety or production criteria, the system isolates a single sweet spot with the highest mathematical probability of success. The AI has effectively distilled millions of data points into a single, verified target. The ultimate function of this digital environment is to replace traditional guesswork with high-probability simulations. Even with this predictive power, the AI is an advisory tool. It does not initiate drilling on its own. It serves as an augmented intelligence for the specialists in control. Human geologists and engineers review these final models, interpreting the AI's results to authorize the final drilling coordinates with a high degree of confidence. Once that target is authorized, the operation shifts from digital planning to physical execution. Surface rigs are deployed to reach the exact coordinate identified by the model. But hitting a precise digital target thousands of meters underground is a different challenge entirely. How does a physical drill bit steer itself through kilometers of solid rock with such precision? Mapping the subsurface has removed the blind spot, but reaching the prize requires a new kind of machinery. The era of digital geology leads directly into the next phase, autonomous drilling.